Now let's put costs on these operations. How much time and space do they take and why? This table lists the cost of each binary tree operation and the reason for it. Any traversal, whether pre-order, in-order, post-order, or level order, costs big O of n. That is because every node is visited exactly once. The recursion also uses call stack space of big O of h. That is the depth of the deepest pending recursive call. Searching for a value in a general tree costs big O of n. There is no ordering to help, so you must check every node. Height, size, and count leaves each cost big O of n. Each one is a full traversal that combines the children's answers. Level order also needs extra space of big O of w, where w is the tree's widest level. The queue can hold up to one full level of nodes at once. Be careful with one thing. The height h and the node count n are not the same thing. How they relate depends entirely on the shape of the tree. A tree is height balanced when every node's two subtrees differ in height by a small constant. In that case, h is about log base 2 of n. But a chain, where every node has just one child, gives h equal to n-1. That is still a legal binary tree by every rule in this chapter. And shape alone gives you no guarantee either way. Nothing in this chapter keeps a tree balanced. Now why that matters for memory. The recursion goes exactly as deep as the tree is tall. The call stack holds one frame per level, so the space is big O of h. A balanced tree of 1,000 nodes stacks only about 10 calls. A 1,000 node chain stacks 1,000, deep enough to overflow the stack on the very same number of nodes. That gap is exactly the reason for Chapter 10. If an ordering rule lets us decide at each step, go left or go right, instead of checking every node, then search drops toward big O of h instead of big O of n, but only once we add that rule. A plain binary tree gives you the shape. Chapter 10 adds the rule that makes the shape pay.